let me speak to some of the mistakes I'm seeing. There are two stages to this problem, and I've specifically picked them out. So there is the stage here between these two where the block makes it to the ramp and starts to climb the ramp, right? Because it's got its own momentum and its own inertia, so it keeps going up the ramp. While that's happening, while the block is going up the ramp, it's pushing on the ramp, speeding the ramp up. And eventually the block will make it to a height where it's no longer moving with respect to the ramp. That phrase okay with you guys? So what that actually means is the ramp and the block will have the same speed. That's when it's at the maximum height. That's a momentum question. And this V, we'll just put V final for lack of a better term, is not the ultimate velocity of the ramp. When the block slides back down the ramp, it is continuing to push on the ramp to the right, speeding the ramp up. So V1 here will be faster than the velocity of the ramp and the block together. So those are not the same velocity. That is a separate part of the problem when the block slides back off the ramp. So focus on finding this velocity, yes, but that can only be used to find the height. Now, if you want, most people have found already that VF equals 1/4 V naught. Does anybody need help seeing where that came from? Okay? So to find that, we're going to use conservation of momentum. And we're going to compare the momentum of this system with the momentum of this system. Okay, we're going to compare the two momentums. So the momentum initially is going to be just the momentum of the block because it's the only thing that's moving. So that's going to be mv naught. Then the block climbs up the ramp, and for a moment the block and the ramp have the same velocity. So the momentum of this system will be the mass of the system times the velocity of the system. They all have to have the same velocity because at this instant the block is at rest with respect to the ramp, but the two objects are moving to the right. So this is just 4 mvf. So cancel the m's and divide by 4, and I find that this final velocity equals 1/4 of the initial velocity. Now that's the conservation of momentum part of this. That doesn't give you the height though. To get the height, you have to realize that in this problem, energy is also conserved. Now, when I say energy is conserved, what I mean by that is that the energy of the system here, with just the one block moving, has to be equal to the energy of the system here, where both the block and the wedge are moving, because there's no losses of energy to the outside. So you have to compare all the different energies that exist. This is to figure out the height of the block. Now what this is going to give us is how high the block is above the reference level. That's what we're looking for. Now what kind of energy does the system have when it's just the one block moving? Kinetic energy. And that is going to be 1/2 mv naught squared. And what kind of energy does the system have when the block makes it to the maximum height on top of the wedge? How do we know it has gravitational potential energy? It's above the reference level. That'll be mgh. Is there any other form of energy in the system? How do we know that there's kinetic energy in the system? All right, we know it's because the block and the wedge are moving. Anything that's moving has kinetic energy. Now the block and the wedge, they have the same velocity. So I will combine them as one object with kinetic energy equal to 1/2 total mass times their velocity squared. This would be V final squared, which we already know to be 1/4 V naught squared. We good there? Okay. This will be 4m and 1/16 v naught squared, right? So that's going to end up being 1/8 mv naught squared, right? A 4 cancels with the 16, and then 1/2 times 1/8 is 1/2 times 1/4 is 1/8. So this is still 1/2 mv naught squared, but all of this ends up being just 1/8 mv naught squared. Subtract it from both sides, cancel out the m's, and I'll get 3/8 v naught squared equals gh. Again, this is just the algebra, but we're just solving that for h. It's one of those things, though, how do you know you're right? It just looks like a bunch of letters. V naught's meters per second squared, and g is meters per second squared. So the square seconds cancels out, one of the meters cancels out, and our units are in meters. So that seems like we probably are on the right track because our units worked out correctly. All right, well, we got the height. Yay. Ready to move on to the next part? We don't need any of this anymore, so we'll just make it small and stick it up in the corner. And we don't really need this anymore either, so we'll stick that over there in that corner. And we don't need this anymore, really. All we need to consider is this and this. You see, because right now, all we really have is a elastic collision. We're no longer dealing with a problem in which we have, potential energy stored anywhere. The blocks conserve energy during this collision, so none of the kinetic energy is lost. So if we want to figure out what V1 and V2 are, we're going to have to treat this as a standard elastic collision, which means mv naught has to equal mv2 plus 3m v1. The problem with this is that it just generates one relationship, but there are two unknowns. So we need more information. Well, it's an elastic collision, which means the kinetic energy is also conserved. That means the kinetic energy of just the block by itself will have to equal the kinetic energy of the block after the collision, plus whatever kinetic energy the wedge takes with it after the collision. Now, V naught and M are allowed to be in our answer, so you have to solve this for V1 and V2. Now, I'm not going to do that, by the way. That sounds like a job for an algebra student, and that's you guys. But I will suggest a couple of things on how to do this solution. First, simplify. There's always going to be some simplification that will occur, so do as much simplification as you can. I'm going to notice that all these terms have an M, so I'm going to cancel out all the M's, and all the kinetic energy terms have a 1/2. So I'm going to get rid of all those 1/2s. And when I do that, I'll get m v naught equals, wait, I'm getting rid of the m's, Mr. Shelton. I'll have v naught equals v2 plus 3 v1. And I'll get v naught squared equals v2 squared plus 3 v1 squared. Now, I'm going to slide this up a little higher. There's only one way to do this, right? Substitution. You solve one of these for V1 or V2 and plug it into the other. But have foresight. You guys are supposed to be mathletes, some of you. I saw the stupid boxes of chocolate. Think it through. It's a quadratic, isn't it? Which means 2 answers for V1 and 2 answers for V2. But you already have a set of answers. V1 is the velocity of the wedge. And it has 2 velocities. It has the velocities before the collision and the velocity after the collision. And so V1, one of the answers is 0. And V2 also has 2 answers. There's the velocity of the block before the collision and the velocity of the block after the collision. So one of the answers for V2 is V naught. Now your job is to find the other answer. But if you have to decide how to do that, I'm telling you right now, since we know that one of the answers for V1 is 0, eliminate V2. Solve this for V2 and plug that in here, because you know that one of your roots will have to be 0. If you do it the other way, one of your roots has to be V naught. That's not necessarily hard, but it's probably easier if you can work a 0 in. And you can. So work the 0 in. Now, we're not going to do the math. We're not going to use class time for that. This is just algebra, and it's not worth the time. Lose your point if you don't know how to do the algebra. But if you don't know how to do that algebra, practice. It's not terrible. All right? We have a few pieces of information. So we know that this is length L, and the table is h high. This is m, and this is 2m. Ready to begin? All right, so I see first that there's a conservation of energy problem that has to be solved first. The block is changing its height. That's how I know that that's probably the best place to start. This would give me the blocks that's on the pendulum. So I'll use the word pendulum there to describe it. The pendulum has potential energy right now, and when it swings downwards, it will convert all that potential energy to kinetic energy, if I choose that the tabletop is the point of reference for measuring energy. That will give me how fast the 2m block is traveling just before its collision. So I'm going to isolate that part of the problem to figure out the speed of the 2m block when it swings to the bottom. So right now, in its current state, the gravitational potential energy of the block is going to be 2mgl, right? Mass of the block, g, and how high it is above the reference level. Any question about that? All right. Well, it swings downwards until it's right there, and now it's got some velocity. I'd like to figure out what that velocity is because it's about to be involved in a collision. So I'm going to set that equal to kinetic energy, which is 1/2 times 2m times v. I'm going to put naught here because this is the first thing that has velocity. So v naught squared. All good for you guys? All right. So we can use this to figure out how fast it's going at the bottom. The 1/2 and the 2 cancel out. The m's cancel out. And I'll get 2gl equals v naught squared. So v naught equals the root of 2gl. And that's how fast it's going when it makes it to the bottom. Going to tuck that away. A collision takes place next. You guys see that? A collision is the instantaneous moment before the collision and the instantaneous moment after the collision. Now, unfortunately for us, after the collision, because I know it's happening before the collision, the momentum before the collision is just going to be 2m v naught. Right, that's the momentum before the collision because the other block has no momentum. But the momentum after the collision is going to be the momentum of the pendulum, because it's still moving after the collision, plus the momentum of the block, because it's now moving after the collision. Does that make sense? Now, I need this velocity, because this velocity represents the horizontal velocity of the block that's about to become a projectile and land on the ground. I need that velocity. Unfortunately, I don't know this velocity. But I do know that the box continues to swing after the collision. All right, so this box is over here someplace doing the projectile thing. And this box continues upwards until it makes it to theta. Right? What kind of energy will the yellow block have? What will the pendulum have when it makes it to its next highest point? Gravitational potential. So I think I can figure out this velocity by figuring out how high the block swings. That's another conservation of energy question, right? But this is the energy of the system after the collision, which is going to be less than the energy before because it was an elastic collision. Block does not swing all the way back up to where it was. So we'll have to do that in a separate process, which I'll do over here. The kinetic energy of the pendulum after the collision will have to equal the gravitational potential energy of the pendulum after the collision, assuming it swings up and stops. That all good for you guys? It's going to get messy. 1/2 times 2m times vp squared has to equal 2m. What am I doing? 2m g L times 1 minus cosine theta. Right? It swings upwards. We're allowed to use theta in our answer. And this is how you figure out the height of the block above the reference level when you have something that's swinging like that. Any questions about those choices? Yep.
Can you explain one more time why you did L parentheses 1 minus cosine theta?
Yes, I can. And I can do it patiently. However, I will promise that this will be the last time. Take accurate notes. Because I know you're not the only person who needs to ask this question, because I was asked this question 3 times this morning, but we talked about it. So I'm going to try and draw it nice and cleanly, but please commit this to memory. I asked that the last time, I'm asking it again. This is the down state. And you'll notice I am trying to be very careful to draw this to scale so you can cleanly see the trig that's involved here. So is it clear that this L and this L are the same? Okay. My baseline is here. Height is that. Well, I guess we'll go from the middle. So this is the height. That all good? Okay. Take a look at this line, please. That's roughly from the middle of the block back to the other side there. Everybody following along? Do you see a right triangle here? I hope so. I will attempt to identify it again for you. But there appears to be a triangle right there. And in this triangle, this right here is the adjacent side. Do you agree with that? So that's the adjacent side, and this is the height. Can we see that the adjacent side plus the height is L? Okay, so adjacent side plus height equals L. But the adjacent side is L cosine theta, if theta is here. So L cosine theta plus H equals L. So H equals L minus L cosine theta, or H equals L times 1 minus cosine theta. It's a trick. Commit it to memory, please. Shows up a lot. Explained thoroughly? Excellent. With due patience and everything? Excellent. All right, so back to this travesty of a problem, but let's keep going with it. I need to figure out how fast it's going. I can cancel out the two m's. So 2 m's are gone. There's nothing pretty about this. VP squared equals 2GL 1 minus cosine theta. There's nothing particularly pleasant about that, but that's what we got. So VP equals the square root of this mess. This is just a mess. 2GL times 1 minus cosine theta. What an algebra nightmare. All right, these have to be equal. So 2mv naught, which is the square root of 2gl, has to equal 2mvp, which is the square root of 2gl times 1 minus cosine theta, plus mv box. Yay, look how pretty this is. All the m's cancel out. That's nice, right? So we cancel out all the m's. And we get 2 root 2gl minus 2 root of 2gl times 1 minus cosine theta equals VB. Yahoo! We now know how fast the box is going after the collision. And that is the horizontal velocity of the box. I'm not sure where to put this next part because this is just like looking like a mess, but maybe it might be worth it just to do that, because now the only part of the problem that we're dealing with is the projectile portion of the problem, where the box, starting from a height of h, has a velocity vb that is purely horizontal. And it's going to fall to the ground as a projectile. So, bonk, like that. This is a projectile motion problem where we have vertical and horizontal. Delta y is h, acceleration is g, vy naught is 0. I would like to find out how long it's in the air. And I don't know if you guys have just thought of doing this, but every time we've done this, this is the square root of 2h over g. Could you just commit that to memory? When you drop something, this is how long it takes to reach the ground. I mean, you can go through the process of delta y equals 1/2 at squared plus vy naught times t. You can do that every single time and get your h equals 1/2 g t squared. But you're still going to come out to the root of 2h over g if you're just dropping something to the ground. So range equals all of this, that plus that, all times the square root of 2h over g. And that's your answer. Easy peasy lemon squeezy. Okay, minus. I was running out of time because the bell rang, signaling the sad time when you guys leave and you're no longer here with me, and I feel bad that I won't see you until tomorrow.